Company Investments and Project Management. This is Chapter 8, Part 1, Following are the Learning Outcomes. After going through this presentation, students would be able to apply capital budgeting to project management decisions, interpret the use of payback period and discounted payback period to find out whether a project is useful for a company or not, apply the concept of net present value to decide whether new projects should be adopted by the company, and analyze new projects using the concept of a rate that is called the internal rate of return. Later on, we will learn some more concepts of how to use and apply net present value into real-world problems, several little applications, and we'll also study what's called as a profitability index to determine whether a project, when we have multitude of projects, which project is the best with respect to the best NPV per investment. So, broadly speaking, this chapter is concerned with what is called as capital budgeting decisions. What is capital budgeting decisions? Capital budgeting decisions are decisions that are large, usually large in magnitude with respect to the dollar value of the initial setup cost. The decisions pan out typically over a few to several years and carry significant costs, like I just mentioned. So the dollar value is typically pretty large. And we also need significant information about not just the company that is adopting the project, but also about the project in general over several years in order to make a correct decision whether the project should be adopted or not. For example, an infrastructure setup cost or a new plant and machine adoption, and what are the returns that we will receive in terms of cash inflows because of this. So the overall picture of capital budgeting is there is typically a setup cost at the beginning and cash inflows that follow after the project is being set up. Now, the first application of how to find out whether a project should be adopted or not is called the payback period. Payback period is an application which is a very simple back of the envelope calculation. The other method is called a discounted payback period. Now we're going to study these one after the other. So the next method that we'll study after that is called the net present value. And the fourth one that we'll study is the internal rate of return. Later on in another presentation, we'll be studying what is called as the profitability index. So these are broadly speaking methodologies that are applied to determine capital budgeting decisions, which method should be adopted, which project should be adopted, which project should not be adopted, and under what circumstances. So now let's study what's called as a payback period. So payback period is a very simple, like I said, back of the envelope method. It treats all cash flows equally. Again, there's a simple setup cost, and subsequently there are cash inflows. And the real principle is in how many years can those cash inflows be able to pay back the initial setup cost, assuming no discount rate. So the comparison is between cash outflow initially and cash inflows later on in the future. The real idea here is in how many periods can the nominal value of the cash outflow be returned to the investor. So to study an example, let's assume we purchase a new commercial jet for $300 million. And to do that, we are employing this because we expect profits or cash flows in the future periods. And these cash flows, let's assume, are not revenue, but let's assume cash inflows of $20 million per year for 25 years. So really the payback period is what? In how many years at the rate of 20 million can we recoup the 300 million of the initial setup cost? And so the payback period is basically 300 million, that the initial setup cost divided by the cash inflow per year, 20 million. So the answer is 15 years. Now there's an elaborate way of doing this in Excel. So let's see that. So let's assume that we spent minus 300 million, and then this is t equals 0, and then this equals this plus 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 12, 13, 14, 15, 16, 15, 20. All right, and it was 20, so equals this, and then go up, black cross, double click. And so what we could do is, the way we can determine the payback period, so we'll just say here payback period method. So equals up arrow plus the cash inflow. Notice how we're not discounting the cash flow here with any interest or discount rate, just adding a nominal value and dragging it all the way down. So really the payback period here is this particular period, 15th period. So in the 15th period, our net value of the project becomes 0 nominally. So assuming all cash flows have the same standing today at t equals 0. So the payback period for this particular project is 15 years, which we also found out by just simply dividing the initial setup cost by the cash inflow per year. So like we just noticed, there's a problem with this method, and the problem is it ignores the cash flows afterwards. So here we still have cash inflows after the payback is done. And so suppose if this cash flow was 150 million, the payback period still remains 15 periods. But really the project becomes more valuable if we have these huge inflows coming in towards the end. And so how do you account for that? We don't know. We'll find out. So the second thing is it ignores time value of money, and discounted payback is exactly what now factors in the time value of money. So cash flow today, as we know, is not equivalent to cash flow either yesterday or cash flow tomorrow. Cash flow yesterday was more valuable and cash flow tomorrow is less valuable. So we need to discount these cash flows in order to compare. So the payback period may provide a more robust looking solution whereas it's really not that robust. Maybe it's, if we account for the time value of money, the project might not look so appealing anymore, as we'll see with the project that we are doing here. So let's just try the same example. Now let's introduce a discount rate of 10%. Going back, so this was a payback method. Now we're going to call this the discounted payback method. And the rate of interest discount rate is 10%. So equals this divided by parenthesis 1 plus 10% to the power of the time. Same thing here, but here what we do is plus previous. So now the value is decreasing, but as you noticed, it is not decreasing that fast, or increasing in a negative sense, increasing but not increasing that fast. So the discounted payback period method says that cash flows further out are no longer that useful. So let's just make it 20 again. No longer that useful. So see, we have not been able to pay back this project even in 20 years. So that's what we meant when we said that the payback period might paint a too robust and rosy picture of a project which actually might not be that useful at all. So discounted payback period will be the time period when this project will reach a value of 0 for the first time. Let's try 50 periods. A50. Shift control up, control V. And no, it's not 50 periods, so 49 and 50. And then copy. No, we have to include the cash flows as well. So everything. Copy. Paste. Wow. As the cash flows become less and less valuable, the project is not able to pay back itself. It's just diminishing. In fact, if you see this graph, it looks pretty disastrous. So it's not going to reach 300 at all. It's not going to reach $0 at all. So it's not going to pay back itself using the discount payback method. So that's why discount payback method is slightly more superior to the payback period method. Okay, so we just solved that. Now, actually, we can say that if we have these cash inflows at 40, then perhaps we can find a payback period between 14 and 15 years right here for the discounted method. So you really need a little bit higher payback, or sorry, cash inflow in order to justify. But here, the payback method had already gone to between 7 and 8 years. So discounted payback saying between 14 and 15 years. See how it becomes positive from negative? That's between 14 and 15 years. We've been able to pay back for the project's initial cost using the discounted payback method. And if we're using just a simple payback method, it's between 7 and 8 years. All right, let's move on to the next concept of project valuation. It is called net present value. Suppose we have a new investment or a project, such as acquisition of a new aircraft in order to fly it to a new route. So we're just going to talk about that. So we have to spend a lot of capital to purchase the aircraft initially. So there's a huge initial setup cost. And then there are cash inflows. So once we start, when we commission the aircraft to a route and offer a frequency of flying on that route, we have passengers who are paying for it. So we'll have cash inflows from operating that aircraft. So we compare. What do we compare it with? Well, we compare it with not operating at all and operating the aircraft. So let's assume that we invested $350,000 today in some project. Since we invested it, it's a cash outflow or a negative cash flow. Let's assume that this project gives us $400,000 back after 1 year. So what I'm discussing now is the intuitive sense of net present value. We have spent some money today on a project and received some money back after 1 year after unwinding the project. Let's assume the discount rate is 12%. So at time t equals 0, we spent $350,000 as a cash outflow. At time t equals 1, we received $400,000 as a cash inflow. If we discount it by 12% over one period, then the present value of the $400,000 is 400,000 divided by 1 plus rate to the power of 1, because it's just one period. In other words, it's 357,143. So are we better off if we invest in the project as compared to 350,000? In other words, is the project giving us the present value of the project inflows? Are they better than the present value of cash outflows? Indeed, they are by 7,000. So 7143 is called the net present value. Now we can always make this much more complicated. So with multiple cash flows, it does become slightly complicated. But we have Excel to our help, so we can easily calculate that in Excel. Now let's assume MKZ Airlines spends $1.5 million for the creation of this new connection. So the input cost or the setup cost is $1.5 million. And MKZ Airlines, so it purchases jets, hires crew, etc., and creates certain infrastructure. And then its expected cash inflows are $164,220.75. Now there's a reason for that 0.75, which we'll see a little bit later. Why we have that number and not just a nice, robust looking number. And this cash flow inflow is growing constantly at the rate of $35,000 per year. And the project is completely wound up in 8 years. The infrastructure is liquidated, the jets are sold off, etc., for no scrap value. Assuming the useful life of that, it's not that, but let's assume that for now. Now, let's also assume the discount rate is 7%. So what we have to really do is compare the cash outflow of 1.5 million with the present value of the cash inflows that are growing constantly. So that's what our challenge is, to find out the net present value. Let's do it. So here we'll just copy these from here to here. So we just have 8 periods. At time t equals 0, it's minus 1.5 million. At time t equals 1, it is 164,220.75. And then this is growing at a constant rate of 35,000. So let's just add this plus and fix it. So $I$3, $I$3. And then control D, control D, control D, control D, control D, control D. That's how we have laid out the cash flows of the project. So our challenge was to find out the net present value at 7%. Now, let's watch this carefully. The formula we use is NPV function. Zoom out a little bit. So it's equals NPV rate, and then we have the range, right? The values. So, but you have to be careful here. The values we choose start at first period, because do we need a present value for a cash flow that is already available to us today? No. So we are only trying to find out the net present value of the cash flows that are in the future. But that doesn't mean we ignore the cash flow today. So NPV function, the arguments are future cash flows, but we also spent some money, namely $1.5 million. So that's the H2 after the NPV function. Now, this has to be converted into a dollar value, and then the row width has changed, so Alt OCA. So the present value of this set of cash flows at 7% discount rate is $138,000. Now, again, let's go back to the previous example. Because the net present value was 7143, it was greater than 0, we said that the present value of cash inflows is bigger than the present value of cash outflows. Therefore, we accept the project. So if we do a little bit of an NPV profile, at what discount rates are we supposed to accept the project and at what rates not? It's going to be a very intuitive answer. So let's start with a rate of 2% and then add a rate of 1% on top of that. So 2%, 3%, 4%. Let's go all the way to 14%. Maybe let's go to 16%. So what are we doing here? This is the discount rate. And then we are finding out the net present value corresponding to that discount rate. So equals NPV rate, comma, range. So there are 8 cash flows, and we fix that using the function F4 key. So it is $H $3 colon $H $10. We've selected the range, and then plus the initial cash flow $H $2. And as we copy it down, again the same problem, we just do Control D because the range is fixed now. By putting those dollar signs, we can just easily copy the formula down. Notice how at 9% it becomes nearly 0. And the picture or the graph that we can obtain, zoom out a little bit, make it 100%. So we can actually plot this net present value against the discount rate. What do we observe? We observe that as the rate increases along the x-axis, the net present value is decreasing, and it hits, well, we can actually format this axis to change it by 1%. 1%, press enter. Oh, major unit, 1%, thank you. Nope, not listing. Okay, make it bigger, maybe it'll listen. There you go. At 9%, the net present value is 0 for this project, and that's what we learned. So let's just recapitulate. So the table of cash flows is here. At 7%, we accept the project because its net present value is bigger than 0. And about other rates, what we saw, that as the discount rate increases, cash flows further out become less valuable, and therefore the initial setup cost, that negative thing, becomes much more expensive, and therefore the net present value goes down. And that's what we see on the graph. The net present value is decreasing as the interest rate are increasing, the discount rate are increasing. This is called the NPV profile, and the rate, the net present value is 0 at the discount rate of 9%. This particular rate is called the internal rate of return. It is that rate of discount at which the net present value becomes 0. Internal rate of return. So internal rate of return is a discount rate at which net present value is 0. So how can we find out internal rate of return without doing this hocus pocus in Excel? Well, just use the IRR function. IRR and the cash flows. Boom. Internal rate of return is 9%. Notice how this yellow cell actually matches this yellow cell. And what we learn is net present value is nearly zero. It's probably 9.0 something. So we can actually find out using increasing the number of decimal places. No, it's actually pretty close to 9%. It's good. So that's called the IRR function. Now, the greater the IRR, the better the cash flows look like. So for example, just a quick experiment. Let's increase this cash flow in this green cell. From 409,000 to 500,000. Notice how the net present value and the internal rate of return, both in cell H11 and H12, will go up. And very nice, right? So the net present value increased, as did the internal rate of return. So again, reverting, you can see how the net present value was lower and the IRR was lower. As soon as I increase the cash flow, the project became more valuable. Its net present value increased. Its internal rate of return increased. So that's how we can use NPV and IRR to make a decision. To conclude, payback period is simple. It is fast, but it does not make economic sense at all times. It ignores the cash flows after the cutoff date and does not consider the time value of money. Discounted payback period actually is superior slightly because it considers the time value of money, but it still ignores the first cash flow after the cutoff date. So later cash flows that are later on after the cutoff date, meaningless. Net present value gives value to those cash flows as well, as we just saw. As we increase those cash flows, NPV goes up, IRR goes up. NPV is a dollar value, and it just makes anything that is positive makes economic sense to adapt. Anything that's negative, reject. So that is the NPV decision-making rule. It considers all cash flows, but distant cash flows are less important. They are important, but not as important. Internal rate of return gives us a percentage or number. Higher that number, better off the project is. So it provides a single measure of comparison. Particularly CEOs and top managers like the IRR because it gives you a single percentage number. So again, the intuitive significance of IRR is it is that discount rate at which the NPV graph crosses the x-axis. That's chapter 8, part 1. Thank you for listening.